In the last section of 4.4 optimization problems, we're going to look at a few more challenging examples in relation to max-min problems. And our next example has a Norman window, has the shape of a rectangle surmounted by a semicircle. If the perimeter of the window is 16 feet, find the value of x so that the greatest possible amount of light is admitted. So if the greatest amount of light is admitted, that means that we want to try to maximize the surface area. Okay, so that's what our goal is. Okay, and we know the perimeter of the window is given to us as 16 feet. And we know that this distance right here, they labeled as x in the diagram. So we're going to start with a let statement. We're going to say let x equal the width. And we're going to let L represent the length. Okay, and the length is going right up into this distance here. So this right here would be L. And then we have a semicircle up here. Okay, and the radius of this semicircle is going to be 1/2 of x. If the whole width of the rectangle is x, then the radius is 1/2. Okay, so now we need to come up with a formula, first of all, for the surface area. And the area of the Norman window is going to be the area of the rectangle, which is going to be x times L, plus 1/2 of a semicircle, which is 1/2 pi r squared. Okay, and the radius is 1/2 x, so this area formula is going to be x times L plus 1/2 pi times x over 2 squared. And if we simplify this, I'm going to get x times L plus, if I square this, it's going to be pi x squared. 2 squared is 4 times that 2 is going to be 8. So there is my area formula for my Norman window. Okay, so I also know that the perimeter of my semicircle is equal to 16 feet. So that's going to give me the second formula. Now, if I think about the perimeter of this Norman window, okay, I have one length of x, I have two lengths of L, and I have half of the circumference. So if I think about the perimeter, it's going to be two lengths, plus one width, plus the half of a circumference. Okay, so the circumference of a semicircle is 2 pi r. So half of the circumference of a semicircle is going to be pi times r. And we know the circumference is 16, and we know that the radius is 1/2 x, so this is going to be pi x over 2. So there is my second formula. Again, a little bit more challenging than the ones that we've used previously. Okay, so now I am going to try to isolate one of the variables, and I'm going to isolate the L in this equation, because if I look back here, L would be the easiest equation to substitute in for here. So I'm going to isolate L. So I'm going to have 16 minus the x minus pi x over 2, and that's going to equal 2L. If I divide everything by 2, I'm going to get 8 minus x over 2 minus pi x over 4 is equal to L. So that's what L is. So I can go back to my first equation, and I'm going to have area equals x times L, which is x over 2 minus pi over 4. Oops, I changed that here. Sorry, I made a mistake. This is going to be 8 minus x over 2 minus pi x over 4. So that's x times L plus pi x squared over 8. Okay, so if I distribute the x here, I get 8x minus x squared over 2 minus pi x squared over 4 plus pi x squared over 8. Okay, so now I could take my derivative at this point right here. So A prime is going to equal the derivative of 8x is going to be 8 minus the derivative of x squared over 2 is simply going to be x minus the derivative of pi x squared over 4, if I bring the 2 out front, is going to be pi x. If I reduce it, it's going to be pi x, or 2 pi x. I'll just leave it as 2 pi x over 4. And in the next step, this is going to be also 2 pi x over 8, which reduces to pi x over 4. Okay, so if we collect like terms, because I do have like terms here, I get the derivative is 8 minus x minus pi x over 4. Okay, and I'm going to set the derivative equal to 0. Okay, so I'm going to solve for x by adding the two x terms to the right-hand side. And then I'm going to factor an x out. And then I'm going to divide by the binomial 1 plus pi over 4 equals x. And if I was to approximate this, this would work out to be approximately 4.48. Okay. Now I have to conclude that or prove that this is we're looking for a maximum because we want the greatest amount of light. So if I take my second derivative, this is going to be my proof. Okay, my second derivative is going to be -1 minus pi over 4. And that is a constant, and it is less than 0. So therefore, my graph is going to be concave down, and my critical number of 4.48 is going to be a relative maximum. Okay, so now the question is find the value of x. So we could say x represents the width. So the width of the window should be 4.48. And just double check the unit here. This was in feet. So that's how wide the window should be to maximize the area. So again, very similar process, but just a little bit more challenging in regards to the difficulty of the problem. Okay, in our next example, okay, we have, let's see if I can make this window a little bigger. There we go. We have a cable television company is laying cable in an area with underground utilities, and two subdivisions are located on opposite sides of Willow Creek, which is 100 meters wide. The company has to connect points P and Q with cable, where Q is on the north bank, 120 meters east of P, and it costs $40 a meter to lay the cable underground and $80 a meter to lay the cable underwater. What is the least expensive way to lay the cable? Okay, so what we're going to do is we are going to set up a situation that let's say that they go partially underground to some point S, and then from S they go across here to Q. Okay, so I'm just going to draw in a dotted line here because we know this whole distance, and we'll call this a point across from QR. We know PR is also going to be 1200, so because it's the same distance as this side on this side of the river. So I'm going to call PS X, and we are going to call SR, obviously would be 1200 minus X. And we know that this side here is also going to be 100 meters because the width of the river is 100 meters. So we are going to let X equal the length of cable underground. Okay, and now we're going to come up with a formula. If you notice here, I formed a right triangle. Okay, and we can say that SQ squared has to equal 100 squared plus 1200 minus x all squared. So if I square root both sides, SQ is going to be the square root of 100 squared plus 1200 minus, oops, that's the wrong place for my bracket. Let's fix that up. 1200 minus x all squared. Okay? So if we want to figure out the cost of the underwater portion, okay, SQ is underwater, so it's going to be 80 times SQ is going to equal 80 times the square root of 100 squared plus 1200 minus x all squared. Okay, so the total cost is going to be, well, I've gone x units under the ground, so it's going to be 40 times x plus 80 times the underwater portion, which is 100 squared plus 1200 minus x all squared. Okay, so now I have my equation, so now I have to take the derivative. So let's just rewrite this here so we have a little bit more space to work with. So there's the cost of the underground portion, and it's 80 times 100 squared. Actually, I'm going to rewrite that actually as 100 squared plus 1200 minus x all squared all to the 1/2. And now I have it in a derivative-friendly form. So if I take the derivative, c prime of x, the derivative of 40x is going to be 40 plus, I'm going to bring the 1/2 out front, and 1/2 times 80 is going to be 40, and then my stuff inside the brackets I'm not going to touch. And this is going to drop to a negative 1/2. And then I have to multiply it by the derivative of the inside. Well, the derivative of 100 squared is 0. And again, this will be a chain rule. So the 2 comes out front. 1200 minus x drops down to the first. And the derivative of 1200 minus x would be negative 1. Okay, so if I clean this up, I'm going to get 40 plus, I have a negative exponent. All of this is raised to the negative exponent, so it can drop down to the bottom of my second term. So I'm going to have 100 squared plus 1200 minus x all squared to the positive 1/2. And then I'm going to have 2 times negative 1 times 40. So I have 2 times negative 1 times 40 times 1200 minus x. Okay, so now I have to figure out my critical numbers. So there's my derivative. So I'm going to set this equal to 0. Okay, so if I get 40 plus, if I multiply these together, that's actually going to become a negative. So let's just change that right away. Okay, so 2 times negative 1 times 40 is going to be negative 80 times 1200 minus x over 100 squared plus 1200 minus x squared to the 1/2. I'm going to set this equal to 40. Okay. And if I add that over to the other side, I'm going to get 40 equals 80 times 1200 minus x all over 100 squared plus 1200 minus x squared all to the 1/2. Okay, so now I'm going to bring this up to the left-hand side by multiplying both sides by, it's highlighted in green. So I am going to get 40 times 100 squared plus 1200 minus x squared all to the 1/2 equals 80 times 1200 minus x. Okay, so now I can divide both sides by 40 because I have a 40 common factor here. So if I do that, I am going to get 100 squared, whoops, plus 1200 minus x all squared. I'm going to put it back to a square root because it was raised to the power of 1/2. And that is going to equal 1200 minus, or 2 times 1200 minus x, because 40 goes into 80 twice. And I have 1200 minus x. Okay, and now we're going to square both sides to get rid of my root. So this is going to be 100 squared plus 1200 minus x all squared is going to equal, if I square the 2 here, I'm going to get 4, and I'm going to get 1200 minus x all squared. Okay, so now at this point, I am going to collect like terms, so I'm going to subtract this guy over to the other side. So I'm going to get 100 squared is going to equal 3 times 1200 minus x all squared. Okay, and now it's just a matter of solving this quadratic equation. So I could divide both sides by 3 to get 100 squared over 3 equals 1200 minus x all squared. And using the square root principle, okay, I am going to square root both sides. So I'm going to get the square root of both sides. So it's going to be plus or minus 100 over root 3, because the square root of 100 squared is 100, and the square root of 3 is root 3, and this is going to equal 1200 minus x. And if I isolate x here, I'll add the x over and bring the 100 over root 3 to the other side. So I'm going to get 1200 plus or minus 100 over root 3, which, if you work out both of these answers, you're going to get x equals 1142, or x equals 1258. And again, x is equal to the distance of the underlying cable if we go back to our original diagram. So the algebra in this one is a little bit crazy, okay? And notice the maximum distance from the two towns is 1,200 meters, so this guy is way too big, okay? So to figure out the maximum or the minimum cost, okay, we have to look at when the part under the water is 0, because that's the least amount I could go. So I have 3 possibilities where I could get my minimum cost. When the distance under the water is 0, when the distance under the water is 1,200, or when the distance under the water is 1142. So this one has a bit of a closed domain. So this is like finding an absolute extrema, okay? And now if I plug these values back into my cost function, which was right here, okay, and you work them out, and I'll let you do the math on your own, but 0, if I plug a 0 in, you end up getting $96,333 to put the cable in. If I go to 1142, it's going to be 54,928. And if I go to 1200, it ends up being 56,000. So the absolute min is right here. So the minimum cost is if you go 1,142 meters under the ground and then go across the water. Again, pretty high level question. not sure if I'd quite give you one like that on a test, but just showing you the application to some engineering types of questions. All right, the last question is one that you could possibly see, okay? And this one says we have a tank with a rectangular base and rectangular sides. Is to be made with an open top, okay? It is to be constructed so the width is 4 meters and its volume is 36 meters. If building the tank costs $10 per square meter for the base and $5 per square meter for the sides, what's the least expensive cost of the tank? Okay. All right, so let's first of all draw ourselves a rectangular tank. Okay, it tells me the width is 4, and we're going to let this be the length and this be the height. So again, let L equal the length. We're going to let H equal the height. And the volume of this tank would be L times H times 4, and we know that the volume is going to be 36 cubic meters. So 36 is going to be 4 times L times H. There's one of my equations. And now we want to figure out the cost of the tank. So to figure out the cost, okay, well, the base is going to have the dimension, the base is going to be down here, obviously, and the area of the base is L times 4. So the area of the base is 4L, and the cost for the base is $10. So I have to times that area by 10. And then it says the cost for the sides is $5. Okay, well, I have two sides that have the area 4 times H. So I have the left and right, so 2 times 4 times H. That's going to give me the area of the sides, of the ends, sorry, and I'm going to times that by 5, plus I have the front face and the back face is going to be L times H, and there's 2 of those, and that's also 5. So if I clean up my cost function here, this is going to be 40L plus, this is going to be 40H plus 10LH. Okay, so now I need to isolate one of my variables from the previous equation. So here I could say that if I divide by 4L, I get 9 over L is equal to H. So I'm going to use this substitution here in my cost equation. So H is 9 over L. So my cost is going to be 40L plus 40 times 9 over L plus 10L times 9 over L. This ends up being 40L plus 360L to the minus 1 if I bring that up, plus 90, because the L's will cancel out in this third term. So now again, I take the derivative, so it's going to be 40. It will be minus 360 over L to the minus 2, which will be L squared, and the derivative of 90 is 0. So now I'm going to set this equal to 0 and figure out what makes it undefined. Well, it's undefined when L equals 0, but that's meaningless in the problem because L is representing a length. So now we're going to figure out what makes the derivative 0. So I'm going to set this whole thing to 0. So I'll add the 360 over L squared to the other side. I multiply both sides by L squared. I get 40L squared is 3,600. And if I divide both sides by 40, I'm going to get L squared is going to equal 36. And if I square root, I get L is plus or minus 6. And because we're dealing with the length, we know we can only have a length of 6. So now I need to do the proof. And for the proof, I'm going to use the second derivative test. So C double prime is going to be, well, remember my first derivative, if I move the L back up to the top, would be minus 360 L to the minus 2. So the derivative of 40 is 0. That's going to be 720 L to the minus 3, which is really over L cubed. And if I evaluate the second derivative at 6, this is going to be positive, therefore my graph is concave up, therefore 6 is a relative min. All right, so let's go back and see what our problem is. We want to know what is the cost of the least expensive tank. So my cost function was right here. And we're just going to plug in. I found out that the L was 6, okay, and I guess I need to find the height. Okay, so the height was equal to 36 over, sorry, height was equal to 9 over L. So the height was 3 over 2, okay, and now to figure out the cost, I can plug into my cost function. So the cost is going to be 40 times the length of 6 plus 40 times the height of 3 over 2 plus 10 times 6 times 3 over 2. This will be 240 plus 60 plus 90. And if I add that up, I get 150 plus 240 is going to be $390 to design this tank. Okay, that concludes optimization problems. Now these last three are a little bit more challenging, okay? Again, your assignment for this section, we're gonna leave this one right now. We might cover this one in class, but your assignment is right there on page 279 and page 214 of the AP text. So give those a try. If you have any questions, you can ask me in class.